This is Unit 2, Video 2. In this video we'll talk about periodic trends. These will be trends on the periodic table. The way the periodic table has been organized is to show you a lot of the trends associated with the elements themselves. So the first trend we'll talk about is ionic character. Now this means forming ions. Remember, ions are charged atoms. An atom technically is neutral, but if it gains a charge it's called an ion. Metals on the periodic table will usually form cations. Now cations is the name we give for positive ions. And make sure you don't pronounce these as cations. Embarrassing me at the dinner table, you actually say ion, cations. And to help you remember that cats have paws. That's why they are positive. The nonmetals then will form anions. Please do not embarrass me and call these anions. Go ahead and pronounce the ion portion of it distinctly. So anions, which are negatively charged. And then hydrogen here, it says forms usually a +1 ion. Remember we said that hydrogen acts like a metal and a non-metal. Well, chemically it acts like a metal, and all metals form positive ions, and that's why hydrogen is thought to be acting like a metal. Now there are exceptions to this, but this is usually the rule. The elements, when they form ions, will actually lose or gain electrons to achieve a noble gas configuration. This means, we mentioned this, every element wants to be like a noble gas in its electron configuration, and they'll react with each other based on how likely or how they can become a noble gas. So here, for example, is a sodium atom. Now the sodium atom has 1 electron in its outer shell, shell 3. And here's a chlorine atom. Chlorine is, you can say, missing 1 electron in its outer shell, shell 3. And so sodium will actually lose that electron and chlorine will gain that electron. And the famous reaction between metallic sodium and gaseous chlorine gives you sodium chloride, which is table salt. And then these, as they lose electrons, they'll be charged, or gain electrons, they'll be charged. So this is kind of the picture using a Bohr model of what happens to elements when they react on the periodic table. So we can ask a similar question. We can ask about lithium. We can use the periodic table to actually predict the charge of lithium, oxygen, and aluminum. So let's go ahead and do all 3 of them. And we'll have to have a periodic table for this. So here is lithium, element number 3. Now lithium, the question is, which noble gas is lithium closest to? Lithium is element 3. The closest noble gas is element 2, helium. Now to become like helium, lithium will lose 1 electron because it has 3 and helium has 2. So as lithium loses an electron, here's lithium, as an electron is taken away, lithium will actually become +1 because electrons are negative. So if you take a negative away, you become positive. So lithium actually forms a +1 ion. The next one is oxygen. If you take a look at oxygen, element number 8, which noble gas is it closest to? Remember, these are the noble gases again, and that would be neon. Oxygen is closest to neon because neon has 10 electrons, oxygen has 8. It's too far for it to go to helium because that will be 6 electrons away. So oxygen will actually gain 2 electrons. Now as oxygen gains electrons, it becomes negatively charged because electrons are negative. So we write the charge again in the upper right hand corner. Oxygen will have a -2 charge. This is actually the most common charge of oxygen. To kind of see this, famously, oxygen forms H2O, and here you have 2 hydrogens balancing each oxygen. The reason for this is because hydrogen is +1, you get 2 of them, and that balances the -2 of the oxygen. And we'll see a lot more of this in a future video. And then finally, the third one was aluminum, I believe. And aluminum here is element number 13. The question is, which noble gas is it closest to? Some want to make you go this way because argon looks like it's closest. However, aluminum having 13 electrons is closer to neon, which has 10 electrons, because that's 3 electrons away. If you go to argon, that'll be 5 electrons away. So aluminum will actually lose 3 electrons to become like neon. And as aluminum loses 3 electrons, it becomes a +3 charge. And that is how you use the periodic table to predict charges. Now, I should say this, if you take a look at, say, the group 1, as we've talked earlier, you see that all of them actually form a +1 charge, because all of them will lose 1 electron to become like the previous noble gas, because they're just 1 electron away from the noble gas. So groups actually have the same charge. Same thing for the oxygen group. All of these guys will gain 2 electrons and form a -2 charge. So that is actually one of the patterns on the periodic table. So go ahead and try a few of these yourself. Now, valence electrons, which we've mentioned, are also shown on the periodic table, and there's a definite trend. And these electrons, again, are involved in chemical reactions. Valence electrons are the outside electrons, outer shell electrons. They are the only ones that will be interacting as 2 atoms come together. We said that these are the S and the P electrons. Remember, the S block is this here, the P block is this here. And so if you take a look, for example, at something like phosphorus, phosphorus has 3 electrons in the P block and 2 electrons in the S block for the 3rd energy level, which is the highest energy level. So phosphorus will have 5 valence electrons. Now, valence electrons are actually represented using dots, and what you do is you put 2 dots on every side of the element symbol, up to 2 dots, and these 2 dots actually represent orbitals. If you recall, we used a line or a box for an orbital, and we put up and down electrons. That's really what this is, and you have a total maximum of 8 dots around each element. So fluorine, for example, right here approaches 8. There's only 1 left, and fluorine is actually right next to the noble gas. So fluorine has 1, 2, 3, 4, 5 in the P and 2 in the S for a total of 7. Now, 8 is maximum because 8 is how many the noble gases have. So that is why 8 is the max. Every element wants to become like a noble gas. So we can go ahead and ask this question: how many valence electrons in each element? And calcium, let's find calcium in the periodic table, element number 20. Calcium is in the 4th shell, and it has only 2 s electrons. Makes it easy, only 2 electrons. Oxygen is in the 2nd shell here, so its 2nd shell electrons are 2 in the S, and then 4 in the P, for a total of 6 valence electrons. Now, this is actually much easier if you take a look at the numbers. On your periodic table, the main groups should actually be labeled. This should be labeled as 1A, this should be labeled as 2A, and then this 3A, 4A, 5, 6, 7, and 8A. And these numbers actually represent the valence electrons. So that's how we get 6. So feel free to use these numbers. Most periodic tables will have them, ours should. Iodine then is right here, and the number above it is 7. So iodine has 7 valence electrons. And then iron, we realize that iron is in the D block. Now if you recall, the D block is 1 energy level less. This is 3D. And iron has 4 s electrons. So its highest shell is 4. So for iron, you'll only count these 2. So iron actually has 1, 2 valence electrons. All the D block elements will have 2 valence electrons, unless you're one of the exceptions. Remember, copper will have 1, and so will silver. So it shouldn't be too bad. And try some on your own to make sure you understand this. And then finally, we'll finish talking about atomic radius. Now, this is kind of the first trend on the periodic table that you can visually see. Now, atomic radius is essentially the radius of the atom. So here you have the atom, and if you measure from the center, from the nucleus to the outside are the boundaries of the valence electrons. You'll see atomic radius. Now, atomic radius is usually measured in angstroms, which is this unit here, and an angstrom is 10 to the negative 10th meters. It's really tiny, but what you could say is that the average atomic radius is actually on the order of an angstrom. So that's kind of the average size of the atom. And you'll see that some atoms are about 2 angstroms. This would be about 2 angstroms. Some are about 1 angstrom. Hydrogen is really small. It's actually lower than 1 angstrom. And we, get pretty big, almost up to 3 angstroms for these atomic sizes. Now what you'll see is a nice little pattern. You'll see that on the left side you have really tall peaks or bar graphs, so you have really large sizes. On the right side you have really small sizes. And this is actually a trend on the periodic table. What you see is a little bit of a dip in the D block, and then they go up again, just slightly. But in the S and the P block, you definitely see a decrease going this way. If we just visually make these into circles, here's what you'll see. Now these are the main group. Remember, the main group are the S and the P block. So you see a definite pattern where going from left to right, you're decreasing in atomic radius. Notice we get smaller as we go this way. Now you'll also see that we increase as we go top to bottom. You actually get bigger and bigger and bigger as you go down. So a definite trend, and this is visually a confirmation of the fact that we have the periodic table arranged correctly. Notice the beauty of the pattern. Now the question is, why is this the case? It's really important to understand why. Atomic radius, here it says, gets bigger as you move down a group. Now remember, groups are vertical columns. So as you get down, these atoms get bigger and bigger and bigger. And the question is, why? And the answer is very simple. It's because of shells. Every time a new shell is started, and a new shell is further from the nucleus. You have the 1s, 2s, 3s, 4s. Each one of these is progressively farther away from the nucleus, making the atom bigger. Now, a similar story happens when you go to the right. Here it says atomic radius gets smaller as you move across a period. Remember, periods are these horizontal rows, so this is period 1. Electrons are filling the same shell, whereas going down you were filling different shells. Here you're filling the same shell. So for example, if you are in shell number 3 and electrons are filling this shell, we're filling shell 3 as we go all the way across the periodic table. And then after argon we start a new shell. So because we're filling the same shell, the nucleus actually increases. So here what happens is the number of protons is increasing. Sodium has 11 protons, magnesium has 12 protons, aluminum has 13, silicon 14. So the nuclear charge is actually getting stronger and stronger because we're getting more protons in the nucleus. And these protons have a pull toward they pull the electrons. The reason why the atomic size is the way it is because there's a pull of the electrons by the positive nucleus. And so because the nucleus is getting stronger and stronger, the pull is getting stronger and stronger, and the atom is getting smaller and smaller. It decreases in size. And this is because we're adding to the same shell. In other words, electrons aren't added to the new shell outside, they're adding to the inner shell, is the idea. So, not to the inner shell, I'm sorry, but to the same shell. The inner shell would be closed off at this point. So that is why, and you must know not only the trends, but also the reasons for the trends. This finishes for us. Video 2, we'll talk about ionization energy next time.